So one of the things that makes vectors so powerful and has so many different applications, like we talked about in the opening episode, is the fact that they are so flexible. There's a lot of different ways to think about vectors, and really you can't just pick the one that works for you and go with it. You really have to learn all of the different ways, simply because different applications lend themselves to thinking about vectors in different ways. All of them obey the same properties, yet there are different ways to sort of visualize what they are and what they fundamentally are represented as, and you have to kind of learn how to be able to think about all those different kinds. So what I'm going to suggest to you in this little segment is that there's a continuum going from concrete to abstract of different ways to think about a vector. And as we move up the continuum from concrete to abstract, it's going to be getting a little bit vaguer and a little bit more general, the way that we're going to think of what a vector is. Whereas lower down on this spectrum, towards the concrete end, it's going to be very nuts and bolts, and you're going to be able to visualize in a very simple way, I see, a vector is just a sequence of numbers that are numbered. That's going to be very concrete. But as we move more abstract, there's going to be different ways to think of it in a little bit more of an ethereal way that turns out to be very, very useful for certain math applications. So let's get started. I'm going to suggest there are 5 levels of abstract versus concreteness. And again, I'm going to put them on a continuum here. I'm going to number them 1 through 5. And most applications where you're thinking about a vector, it's going to fall into one of these things. Again, we're going to be using this notation a lot with a little arrow on top. And at the very bottom here, I'm going to use basically the same example we did in the last segment, something like this, right? Where we have a 2-dimensional quantity here. And this is something where we can readily visualize what this is looking like in a coordinate system. And as I mentioned last time, we can basically put a dot here. Although more often than not, we're not going to put a dot here. Instead, what we're going to do is we're going to draw an arrow from the origin to, kind of got off a little bit there, but I'm trying to point at that point, to the particular point, right? So we would talk about the vector 2, 5 as being this arrow. And I'll talk in a future segment a little bit more about the geometric interpretation there. For now, though, just keep in mind that you could put any point here by defining any 2 coordinates. And we're just going to think of the vector as the arrow that goes to that point or whatever, right? Okay, so that's kind of lowest on the abstract level. Now, we can number these things, and here's going to be kind of a weird wrinkle. Different programming languages use different numbering schemes. Some of them, like R, will number the 2 components of a vector 1, 2, which seems very sensible. There are other languages, however, and Python is one in this class, that doesn't use 1, 2. Instead, it will use 0, 1. So in Python, the indices of a vector, and by the way, that's what those are called. These things right here are called the indices, or the singular's index, into the vector. So I will sometimes use the phrase, we index into the vector and get a value. And what I mean by that is if I say, okay, let's index into the x vector and get the value at index equals 2, then we're going to get the value 5. Okay, so the indexes or the indices are the numbers always in sequence that we're using to get elements out of the vector, and then the element that we get out at a particular index is the element. Okay, so those are terms that I'll use. Anyway, back to R and Python. So these here on the bottom in blue are Python indices, whereas these up here are R indices. And there's actually good reasons to use either one. There's arguments to be made in favor of starting with 1, starting with 0. Actually, to be honest, on balance, I think it actually makes more sense in more situations to start with 0, which may surprise you because you may say, hey, ever since I learned how to count, I started at 1, so what's the starting at 0 business? You just kind of got to get used to that, and that's one of the things that in computer science you just need to nail early on. It's a very low-level kind of tedious concept, but you just got to get the idea around, or get your head around the idea that every time you're talking about an index, you have to ask yourself, am I dealing with a 0-based index like in Python, or am I dealing with a 1-based index like in R? And I will try to always be consistent about telling you which one we're using there. But I'll swap back between the two because we're going to be using both languages in the later segments of this and other episodes, and also because you're going to be using programming languages that use both, so you need to kind of be able to get used to both, right? Okay, so that's like the most concrete thing because we can readily visualize that in a 2-dimensional space. Okay, next one. A little bit less concrete, I could represent this. I could say I've got the vector 4, 3, 2, 9, 6, 7. Okay? And of course, if I numbered these, those would be numbered 1, 2, 3, 4, 5, and 6 if I'm doing R, or 0, 1, 2, 3, 4, 5 if I'm using Python. Reason I say this is more abstract is because we can't visualize this, right? Human beings can think in 2 dimensions and visualize 2 dimensions really, really well. Humans can barely, the good ones, can barely deal with 3 dimensions without going crazy. Anything higher than that, we can't fathom it, okay? Only God can think in a higher number of dimensions than 3. And so once we get to this level where it's more than a 2-dimensional thing, we're basically in the realm where we have to sort of suspend our disbelief and just treat it as some kind of composite object that's composed of 6 numeric elements in order. We can sort of buy the fact that in some sense there is a 6-dimensional world in which this exists as a point or an arrow, but beyond just sort of believing that there is such a thing, we can't really do much more with it than that. And there will be times when we talk about a vector that's this long or longer and we think of it as a point in space, but really, we can't visualize how close it is to other points in space very easily. We can't envision, which direction it's in, because the first direction is left and right, the other one's up and down, the third one's in and out, and then you're sort of lost after that, right? Because there isn't any other thing we can visualize because we deal in a 3-dimensional world. But nevertheless, that is another way of dealing with a vector, and we will definitely have lots of cases where we're dealing with a vector with more than 2 dimensions, and you might ask, why would we do that if we can't visualize it, if we live in a 2 or 3-dimensional world? Well, it's because we're often going to deal with vectors in a way that doesn't relate to geometric interpretations, but which involves something like a time series, say, right? If you want to get Google's stock price every day for the last year, you're going to have a vector of 365 dimensions, or a vector of length 365, and you just sort of throw out the fact that you might try to visualize it geometrically. You just say, hey, I'm just going to treat this as a sequence of 365 numbers, and we can deal with that vector quantity. Okay, next. If I say I've got 4, 3, 2, 9, that looks the same as number 2 on my continuum here, except that now I'm going to say, you know what, I'm not actually going to use numbers at all. I'm going to use names to represent these things. I'm going to say that this is Sam, and this is Joe, and this is Bev, and this is Sue. So you can imagine that maybe this vector is keeping track of what level each of these players has reached in a certain video game, say, right? Or maybe it's the number of automobiles they have registered to them in the DMV database. Who knows what it is? But the point is, now I'm not treating the indices as numbers. I'm not going to say there's any point in saying what is element number 1 or element number 4. Instead, I'm going to say, what is Joe's value? What is Bev's value? Because really, I'm not thinking of it as a sequence anymore. I'm thinking of it as a bunch of labeled points. And now this even less fits into a geometrical picture, but nevertheless, it turns out to be very, very useful in a lot of scenarios. Okay, so that's another way we'll think of vectors sometimes. And yet another way we'll think of vectors is something where, again, we represent them, or index them rather, by names. But now I'm going to say, I don't even have numbers up here. Maybe I have something like red and blue and purple. And now this is a vector representing what everyone's favorite color is. And so now the element itself is not even numeric, let alone the index. And this is another way to think of a vector. And yes, there are going to be things we can do with this mathematically that are going to turn out to be very, very useful for us. All right, so that's the 4th one on the continuum. Almost everything we do in this volume of all the math is going to be dealing with stuff in these 4 levels of the concrete to abstract continuum. We're almost never going to deal with level 5, but I want to tell you about it anyway, because when you start dealing with any higher level math, especially theoretical math, if you look at papers or books that have to do with dealing with very abstract concepts, they will very often make use of vectors, or also another concept is that of a vector space. And when they talk about vector spaces being full of vectors in these advanced mathematical books, they are really talking about things with certain properties. And baby, that's as concrete as it gets when you're at level 5 of this continuum. The idea is they'll say, you know what, we can have a vector, and we don't need to think about it as a sequence of elements with boxes or anything like that. It doesn't have to be numbers. It doesn't even have to be different elements, really. It's just anything that obeys certain properties. We're going to learn that vectors can be combined in different ways. We can take the norm of a vector. We can combine vectors into matrices. We can say, what is the span of this set of vectors? There's going to be a lot of really deep stuff we deal in this class, and we're almost always going to be dealing with those bottom 4 levels of the continuum. However, it turns out to be extremely useful in a lot of upper-level theoretical math to say, you know what, for a moment, let's forget about the fact that there are even elements, maybe there aren't, but we want to define some mathematical objects that obey the same properties that I'm going to tell you about in future segments that are commutative and associative in these certain ways that can be combined in this way. We can define the notion of what a norm is or the notion of what a span is, all those different things, and yet we're going to do it in a completely abstract way where we treat the vector as just a thing. And so, again, if you're mathematically inclined and you go to some more advanced mathematics classes, when you see this, you will hear them use the word vector, and immediately you'll think, right, I took a class that dealt with vectors. Just remember that a lot of the things we're doing in this episode really do actually apply to those kinds of vectors. It's just that they'll never show a sequence of elements because they're not thinking of it that concretely. They're thinking of it as a purely abstract notion.